So this is where we left off yesterday. We were looking at the whole spectrum. Right? The spectrum was all the available frequencies and wavelengths. Okay? And we're talking about light, but light is just a tiny fraction of the entire possible kinds of waves. There are waves we can't see. Fact is, most of the electromagnetic waves we can't see. We can only see the ones that run from red to violet. Okay? Now, what made them different was how frequent the waves came, that these were, come on, do what you're supposed to do. That these were these high frequency waves and those were low frequency waves. Okay? So ultraviolet means above violet. So violet's here, ultraviolet's above it. Infra means below, so infrared means below red. Now we cannot see ultraviolet, but bees can. So the flowers look different to the bees than they look to us. Okay? And we can't see infrared, but there are some snakes called pit vipers that have a sensing organs in the middle of their face that detects heat, detects the infrared. And that's how it hunts mice in the dark, because it can sense the heat. So our sensors, the other animals can detect infrared and ultraviolet. Okay, we can't. Microwave, the stuff that heats up your food, is the same as the light wave, just a different frequency. Radio waves, the way the information is traveling from this microphone to the speaker, is the same kind of wave as light, only a much lower frequency. Okay? So on the bell work, we said we had frequency and wavelength. How are they related to each other? If I make a lot of waves, are those waves going to be long or short? Short. So as the frequency, if I make them more frequently, I'm going to have shorter waves. So as one goes up, the other goes down. So my high energy is going to be a long wavelength, and my low energy, or my high frequency is going to be a short wavelength. Okay, tied close to this, and we haven't talked about it yet, but tied closely, if I wanted to make a whole bunch of, if I want to make a high frequency wave, like I was shaking a string to make waves go down it, if I want to make it high frequency, would I have to put a lot of energy into it or just a little bit? I want to make short waves. I want to make them frequently. Yeah, I'd have to move my hand up and down pretty frequently, right? That's going to use a lot of energy. Whereas if I want to make long waves, I can move my hand pretty slowly and not use energy nearly as much. So if I want high frequency, that's going to be high energy. And if I want low frequency, that's going to be low energy. So frequency and energy go together. They're directly related. Okay, and I like to say this because this right here, we spent time talking about gamma rays last chapter, talking about how they could knock our DNA around. And if they knock the DNA around, it gives us a chance of getting cancer. Okay? X-rays can do the same thing, not as deep. That's why the technician leaves the room when you get an X-ray. Because the X-rays are doing you some good. It's good to know whether your leg is broken or not. But it's no benefit at all to the technician. So they shouldn't be exposed. Is that reasonable? Okay. But when I see that it makes sense that X-rays could go through and knock DNA around, what comes to mind is people say that cell phones are, I hear in the news all the time, cell phones causing brain cancer. And my problem is, how? Okay, I can understand gamma rays and X-rays, penetrating, knocking around DNA, they got lots of energy. But cell phones use radio waves. Cell phones use radio waves. Really low energy. They don't have enough energy to break DNA apart. Their waves can't break DNA. So if it can't break DNA, how's it causing cancer? They may have some correlations, but no one's answered that question. So until they answer that question, I'm kind of doubtful that cell phones are causing cancer. Because it just doesn't make sense that radio can cause cancer. Makes sense that X-rays can cause cancer. Not, yeah. Ever see why I question it? You got to come up with a big mechanism, a completely new way of making cancer that I don't know about. Right. Okay. Okay. Now, light is a particle. Okay. And we'll talk about how they know it's a particle a little bit later. But one of the found is, it actually, we can thank Einstein for it. He figured out that light is a particle. And those smallest pieces of light are called photons. So quanta was the smallest pieces. A quanta of light is a photon. That light comes in little tiny pieces called photons. Notice the ton at the end again, like the names of pieces. So when you see that ton at the end or tron, that tells you it's a piece, right? And photo makes it pretty clear it's a piece of light. See, I can get it right out of the name? A piece of light. That's what photon says. Okay. And like we saw on the spectrum, energy and frequency are directly related. What does directly related mean? Well, directly related means what happens to one happens to the other. And numerically too. If I have twice the frequency, it's going to take me it's going to have twice the energy. If it's 1/2 the energy, it's going to be 1/2 the frequency. Which is the opposite of wavelength and frequency. Because as the frequency went up, the wavelength went down. So twice the frequency was 1/2 the wavelength. I take and turn it over. That's why they call that an inverse relationship. Because you take the 2/1 and flip it to 1/2. Okay, so here is the mathematical relationship between these two. E equals H times, that's another Greek letter, or that's our Greek letter, nu. It's a nu letter. So translated, because every equation is really a sentence, the left-hand side is the E. What is that E? Energy. The energy of the photon. What's new? Now, what's new? New is frequency. New is frequency. Yeah, it doesn't look much like an N, but when you do it handwritten, and then you get some more cursive and starts getting more and more down, eventually you end up with something that looks like our lowercase n. It just got faster and faster at it. Okay? Our lowercase n came out of that. Because they picked n or nu because frequency is the number of waves. They picked it for n, for number. That's why they picked it. Because it takes place of n. And H is called Planck's constant. He's German, so I always have a hard time saying that German soft A. Planck. Right? What do you think is true about Planck's constant? It never changes. It's constant. So it's just a number. Actually, it's really just a conversion factor between energy and frequency. So H is 6.626 times 10 to the negative 34th. And the units are joule seconds. Not joules over seconds. Not joules slash seconds. Joules times seconds. bizarre units, but that's because we just want this to convert energy into frequency. No. So how would you describe that number? Really, really small. So my packets of energy tend to be really, really small. Enough to do things like knock around an electron. Does that make sense? Really, really, really small, so they can knock electrons around. Right? There's the equation. There's the constant. Actually, if you look at this, in chapter 5, there's only 2 equations. We'll do the math this time, but there's only 2 equations. One we learned yesterday, c equals lambda nu. Speed of light equals wavelength times frequency. And the one we just saw, E equals h nu. Those are the only 2 equations. You will notice that there are 5 letters in those 2 equations. You can't solve 5 variables with 2 equations. But 2 of those aren't variables. 2 of them are constants. Because c is constant. It's always 3 times 10 to the 8th meters per second. Always. And h is always 6.626 times 10 to the negative 34th joule seconds. So you notice C and H I know all the time. So in this first equation, if I give you nu, you can figure out lambda. Or if I give you lambda, you can figure out nu. Everybody okay with that? The second equation, since H is always constant, if I tell you H, you can figure out nu. Or if I tell you nu, you can figure out H. You can always solve for one unknown, right? But notice that means that if I tell you any one of these, you can figure out the other 2. Because if I tell you energy, you can figure out frequency. And once you figured out frequency, you can figure out wavelength. Does that make sense? If I tell you frequency, if I tell you nu, you can figure out lambda and you can figure out E. Or if I tell you wavelength, you can figure out the nu and then stick that in there and figure out the E. So I tell you any one of those, you can do the other 2, which says that they're really just 3 different ways of looking at the same thing. So what is a different color? A different color is a different frequency of light, which means it's a different wavelength of light, which means it's a different energy of photon. Because they're all just 3 different ways of looking at the same thing. Because we labeled our spectrum 3 different ways. Right? We had low wavelength, high frequency, high energy. Right? So those 3 are all tied together. So let's work through a few examples before I have you practice this on your own here in class and then esta noche. Okay, and I've actually tried to structure the first few problems on all of these to give you an idea of how to think about doing them. So, Blu-ray, okay? What Blu-ray is they use a blue laser instead of a red laser. That's why they call it Blu-ray. And the reason why you'd want to use a Blu-ray laser rather than a red laser is a blue laser is a shorter wavelength, which means the waves are closer together, which means you can pack the information closer together. So that's why a Blu-ray disc holds more information, is because it can make it can pack it in tighter because its wavelength is shorter. Okay? So they called it Blu-ray, and they were actually being descriptive. It uses the blue laser. All right. So here's how you should think about these. First, identify what they gave you. What did they give me here? They gave me 4.2 times 10 to the minus 7th meters, and that's lambda. That's wavelength. So I want to find wavelength. I've given wavelength, I want to find frequency. That's new. So label what you're given and find so you can figure out which equation you can use to solve this. Can anybody think of an equation that has lambda and nu in it? Yeah, so the formula for this I'm going to use is C equals lambda nu. Except I want to find nu. So I've got to get nu by itself. That make sense? So I got to get nu by itself. So how can I get nu by itself? I got one. I had one. So how do I get nu by itself here? Divide by lambda, right? They're bizarre letters, but if I made them x's and y's that you're used to using, we do exactly the same thing. So I would divide both sides by lambda, and I get nu equals C over lambda. So there's my plan. It took me a long time to get there. You can go through it a lot faster than that, right? Okay. So that's my plan. So I'm going to do this. So nu equals C, and C is always 3.00 times 10 to the 8th meters per second. And I want to divide it by lambda, 4.2 times 10 to the minus 7th meters. And then I push buttons. 3.00 EE8 divided by 4.2 EE negative 7. If you push buttons correctly, you should get 7.14 times 10 to the 14th as a number. Remember, those of you with the multi-view have got to push parentheses around your scientific notation. Okay? What unit? Okay, well, let's go over here. Let's look. I got meters on the top and meters on the bottom, so they cancel out. But it's got seconds, but the seconds doesn't move up top because I got rid of the m. It's 1 over seconds. It's per second, which is another way of writing hertz. Because remember, hertz equals how many per second? 1 over second. Sometimes you'll see it written this way, second to the minus 1. But that's over seconds, right? Anything to the negative 1 means it's on the bottom. Okay? Now, it seems confusing to have two different ways of writing it. Why did they come up with hertz? Okay? Well, next example will show you why they came up with hertz. Okay? On the way to work, sometimes I listen to KFI, which is AM 640. And that 640 is kilohertz. It's how many thousand hertz. And it wouldn't make sense to say kilo 1 over seconds. Is that reasonable that we don't want to do kilo 1 over seconds? So they came up with the unit hertz so they could stick a kilo or in front of it. So you're turning your radio dial on AM, it's kilohertz. When you do it on the FM dial, it's megahertz. How many million hertz? So what were you given? I was given frequency, and the symbol for frequency, because that's important in my equations, is nu. What are they asking me to find? wavelength, which the letter for wavelength is the lambda. Anybody know equation has those two pieces in it? See how going through this process really isolates what we got two equations. I know which one to use, right? So the formula is going to be C equals lambda nu. And now I want to find lambda. So I got it up top already. I just got to get it by itself. So I divide both sides by nu. So that lambda equals C over nu. And then we can substitute. Yeah, so 640 kilohertz, and if kilo means 1,000, that means 640,000 hertz. Okay? So C equals, or no, lambda equals C, which is always 3.00 times 10 to the 8th meters per second, divided by 640,000. And I do not want to write hertz here. I want to write it as 1 over seconds. Remember, hertz equals 1 over seconds. It's the same thing. Everybody see why I wanted to write it as 1 over seconds this time? Because I got seconds on the bottom up top, and I got seconds on the bottom of the bottom. So the seconds are going to cancel out, leaving me with just units of meters, which is a good thing because I was looking for a length. How long is the wave? And I just have to do that division. 3E8 divided by 640,000 equals, I got 469 meters. So I said they come in different size. Those waves come in different sizes, right? Our last wave was 10 to the minus 7th meters, less than a millionth of a meter. This wave is 469 meters long over 4 football fields for one wave. I told you they come in all sizes. We only get to see the ones that are near 10 to the minus 7th meters. 10 to the minus 7th, 10 to the minus 6, 10 to the minus 7, that's where the visible spectrum is at. Okay. All right. What is the energy of a photon of UV light that's got a frequency of 3 times 10 to the 15th hertz? So what were we given? We were given frequency, and the letter for frequency is that nu letter. I was given nu. Asked you to find energy. Can anybody think of a formula that has energy and nu in it? Equals H nu, and I'm trying to find E. Hey, it's already set up for me. Right, see, it's all set up. So I just have to substitute. E equals, H was 6.626 times 10 to the negative 34th joules times seconds. And I multiply that by my 3.0 times 10 to the 8th, or 10 to the 15th, sorry. that not work? Times 10 to the 15th. And I'm going to write my hertz as 1 over seconds. See why I want to write it as 1 over seconds? Because then my seconds cancel out, and I'm left with joules, which is a unit of energy. And so I just have to multiply 6.626 e negative 34 times 3e15 equals, I got 1.99 times 10 to the negative 18th. And the only unit I have left is joules. Yeah, Isaiah, just go ahead and turn it off and give it to me. So, power it all the way down. So it doesn't ring. Power it all the way down so it doesn't ring in the office. All right. So, one last example. Actually, we'll do the next one. What is the energy? You don't have to turn off? Okay, so you hold the power button over here. Oops, yours has got a different one. It's a new one. Oh, I bet you it's this little one buried deep inside. One without the button on top of it. Okay. All right, so what is the energy of a photon of a microwave with a wavelength of 2 centimeters? This is going to be a pretty nasty question. And you'll identify some problems along the way as you're trying to solve it. Okay. First, what was given? What was given was lambda, wavelength. What was asked for? Asked for, wanted to find energy. What formula? Do we have a formula? No. Okay, so because they gave me lambda, I know I'm going to have to use C equals lambda nu. See, I could identify that? Since the only number I have is lambda, I'm going to have to use lambda, and the only equation lambda's in is C equals lambda nu. So I'm going to be able to solve this for nu, because I'll know C and lambda. So nu equals C over lambda. So I can take that lambda and turn it into nu. Now can I find energy? Do I have an equation that has E and nu in it? I got one that has energy and frequency in it, so I'm going to have to use both equations. So once I do this, then I'll be able to do E equals H nu. Does that make sense? How I made those decisions. I know since they gave me lambda, I had to use the one with lambda in it. And that would let me figure out the nu. Once I figure out that nu, then I can figure out the energy. The other way to approach it is, the only way I can find energy is if I know the frequency. The only way to find energy is to know nu. Where could I get that frequency from? The wavelength. Right? So I can start from the beginning. I've got to start with wavelength to get to energy. And the other way, I need energy, so I'm going to need frequency along the way. See how it helps you plan your route between start and finish. Okay, now let's carry it out. Okay, so first I was going to do nu equals C over lambda, and that's 3.00 times 10 to the 8th meters per second, divided by, hey, I'm going to erase this real fast because right away I'm going to recognize this is wrong. Why won't that work? It's in centimeters, right? I got centimeters and meters. I gotta have them both be the same. So I got to fix that centimeters before I put it in there. Okay, and kids hate doing anything during cold mornings. Move it over twice, right? So 0.02 meters. Right? If I take my 2 and move it over twice, or I could have said I want to get rid of centimeters and turn it to meters. 100 centimeters for 1 meter. Divide by 100. Move it over twice. Okay. So 3e8 divided by 0.02 is 1.5 times 10 to the 10th, and that is 1 over seconds. That's my frequency. And now I said I was going to use this equation, so I'll do that. I ran out of room down here, so I'm going to do that up here. E equals h 6.626 times 10 to the negative 34th joules seconds times 1.5 times 10 to the 10th seconds. Oh, 1 over seconds, sorry, 1 over seconds. So 6.626 e negative 34 times 1.5 E10 equals 9.94 times 10 to the negative 24th. And the units, the seconds cancel out and left with just joules, which is the unit for energy. So and that's as nasty as it can get. They give you the wrong unit, so you fix it, and you have to use both equations. And that's the nastiest math in this chapter. So, how would you get good at doing this? By watching other people do it. No, that's not how you get good at this, right? So, here's the practice sheet. For the first few, I put that structure, and I want you to fill out that structure. Okay? I'm not going to guarantee I look for it on the next ones, but it's the way you need to guide your thinking. What do they give you? What do they want you to find? And that'll give you an idea of what equation you're going to end up using. Right? Oops, sorry. Yeah, you were focused on it, Isaiah. Something big's going on. You kept staring at your lap. That's never a good sign. Yeah, there's 10 problems. It's not. Hey, and I would spend, we got 15 minutes. I would spend the first 7 minutes. You have one or question? Okay, I'll talk about, it's your calculator. I'll tell you how to solve that problem. Because you keep getting